So we're looking at how to use Simulink in this video. And we've seen in the class how to build a system block diagram. So we'll just revise that quickly before we jump into the actual Simulink fun stuff. So let's say we're looking at a system that's represented by 6x double dot plus 18x dot plus 36x is equal to 0. Now, I would recommend that you do not cancel these out and make it, 3 and 6 if you divide by 6. The reason will become evident as we go through this video. So the first step is you have x double dot is equal to, and then you move this to the other side, right? So you have minus 18x dot minus 36x. Don't forget that you had this constant here, so then it's 1 by 6. Now we start with the building blocks for this system block diagram, which is you have an integrand, which is represented by this 1 by s. So if x double dot is the input to this, output is x dot. And if x dot is the input to this, output is x. So it's x double dot multiplied with this, giving us x dot. X dot multiplied with this, giving us x. That's in the time domain. This is just for our way of communicating. Simulink sees everything in the Laplace domain. And a system block diagram as well, you typically have everything. You do have to have everything represented in the Laplace domain. So now what we're trying to do is represent this within this. So what that means is this here should be equal to the signal coming in here. And to do that, what we do is we create pickup points from x dot and x. And we now have to multiply that with 18 so that we get 18x dot. Because as you know, a pickup point is taking a copy of the signal, right? And the way we show gain is with a triangle. It's not a requirement. It can also be a rectangle, but generally we see this and it's commonly understood as a gain. So we have these two gains coming in. So this means that x dot is multiplied with this gain. So this signal here is 18x dot. X is multiplied with this gain. So this signal here is 36x. I want to capture the relation between them, which is minus 18 times x dot minus 36x. So we have two negative signs, right? For this and that, because we chose positive constants here. And so now we have this coming in and that coming in. So now the signal that comes out of this is basically minus of whatever was the signal, which is 36x, minus whatever is this signal, which is, minus whatever is this signal, which is 18 times x dot. So at this point, we have created this signal. We want to create this as well. So in this case, we just need the constant to be multiplied. I'm going to try to make that neater by just doing it a rectangle. Just the same thing. Whatever signal is coming in is multiplied by 1 by 6. And basically, this signal here is x double dot, which by means of all of this stuff here, we have made it equal to that. So this entire thing is equal to this. I hope that's clear, and I hope that's a good refresher. Um, I hope this is kind of fun to do because you're taking equations and you're making them a visual representation. And it also becomes very useful when you start doing it, doing system analysis and so on. So I'm just taking a copy of this so I can use it when I build a Simulink model. Um, so when you want to do the Simulink model, you basically have to open MATLAB. This is like just a blank window, and you go to New Simulink Model, and you create a blank model. This is a blank slate for you to build your representation of the system block diagram, which is basically this. So here, I want you guys to pause, and if you don't have a system that allows you to um, build the system block diagram with me, I recommend that you stop and you actually get a system where you can follow along with me because you might have to watch this video again later if you're trying to build the assignment models and so on. So highly recommend pause and try to follow along with me. So as I said, the first step is to build the integrator blocks. So if you just double click on the blank slate and then you type integrator, you get the 1/s. And you have a signal coming in, and whatever the signal is, multiply with this, and that becomes a signal out. So you're trying to build this building block here. So we have two of those integrands. So what I did now is I just moved them together. And because Simulink is nice, it lets you know that you can just create a signal here. So it does that for you. But you can also just drag with your left mouse click, and you can create a signal connection between two blocks. Since I'm trying to replicate this here, basically I just created this now, right? So you can name this signal as X dot. Always a good idea to name the signal so that you know what you're looking at. And what is coming out of this is another signal, which is X. And if you want to also name the signal coming here, you just drag it from that input and you can name it X double dot or D dot. So at this point, you have done this much. And now we want to build the rest of it. So there's no particular order in which you need to do this, but the thing that you have to keep in mind is if you want to create a copy of a signal, you move your mouse there and then you right click, hold, and pull. Okay. So now you've created a pickup point or a takeoff point. I just hit Control Z and it deleted the whole thing. So I hit it again and now it's back. You can select a signal, you want to delete it. So you right click, hold, and drag. So this is now a copy of X dot. And then you can double click any blank space and type in gain. And now you have this gain. And so the gain that is associated with X dot is 18. I'm gonna double click that, type in for the gain 18. And now I would like for it to be pointing the other way simply because I like keeping things clean. So I click the element that I'm interested in and then I hold Control R twice. Keep doing that, it keeps rotating. So I want it to be pointing this way because that's how I drew the diagram on paper. Now I can connect that. So now this signal that's coming out is 18x dot. Now, I don't think you need to name it as 18x dot simply because it's easy to see, it's visual, and also you're more interested in naming signals that matter. So x double dot is the acceleration, x dot is the velocity, x is the position. typically, right? So you name those. And similarly here, we have another signal which we are providing a gain of 36. So these red signals which are dotted basically means that the signal is not complete. So this signal is going to nowhere. It's just that there exists a signal. And now I'm already playing with it. So in this case, when I connect this here, it forms a strong signal until there, while this here is uncertain where it's going to go. But all of this is just X. Okay. Don't worry about the red stuff. As we build it, it'll become solid lines and should be fine. So now we have these signals coming out, and I'd shown how you want these signals to go inside this region, the addition block or the sum block. In general, if you can think of a word that describes the block, you just double click and then you can type add for this case, which is kind of what I drew. But maybe you thought of the word sum and you get this, which looks different, but they're doing the same thing. So in this, you have plus and plus, and this whatever's coming in will be added and it comes out. In some representations, this is favored, but in the one that we are looking at, I'd like to keep it this way. There's no rule to it. So this signal is now coming in here, and this signal is coming in here. Now there's a grave mistake we made, which is that these are actually supposed to be minus. And so if you now double click this, you get the options of signals that are coming in. So you do minus minus, and then you hit apply, it's changed, right? So at this point, we have built this, this. We have this stuff here. And then this here is remaining. So let's do that. So you can do a gain of 1/6. And with that, everything that you need from that hand-sketched system block diagram has been communicated to Simulink. Now, Simulink is always going to be used for something, right? Typically, we are always chasing this X term. We want to know what is the system response. We obtained um, we obtained this equation or whatever was above it, 6x double dot plus 18x dot plus 36x is equal to 0. We obtained that using Newton's laws of motion or whatever physical principles apply and so on. And then if you didn't have access to Simulink, you would have to do Laplace transform, inverse Laplace transform, and in that you end up understanding things about the system. But sometimes you just want to build a system very quickly. And Simulink helps with that. Simulink also helps with nonlinear systems and highly complicated systems where multiple components are linked together. So this is a very simple example. You can easily do this by hand, but for this example, I'll show you how you can use Simulink to just see what is the system response. So in this case, double click and you type a scope. So it's like you're scoping the signal. And now this scope has whatever is X, you can visualize it in this scope. At this point, we have not run the simulation. And let's say I hit run, we get a 0 here. Is something wrong? No. There is no input to the system, right? So it's like your system was 6x double dot plus 18x dot plus 36x is equal to 0. There's no force acting on it. But initial conditions can happen, right? So how do you actually account for that? The way that Simulink handles this is within the integrator, if you double click it, there's an initial condition. So this integrator is the one that gives you x dot. So this is the integrator that defines the initial condition would define what is velocity for this integrator. So let's say that the velocity is 1 at the time of starting simulation. So let's hit OK. And then we're hitting the play button. So much fun. And you see it's starting at 0, that's velocity, and then it comes back down. Now, looking at this response, you should be able to say that the system is stable because it's coming to the equilibrium position and it is not going away towards infinity, which is actually the definition of what would be an unstable system. Let's add one more initial condition. So this integrator is the one before x. So let's say it's initial condition of 1. So there's now an initial condition for the velocity of 1. And just for the sake of it, let's make this 2. So we're starting from a position of 2. So we've not yet hit play. So let's just visualize how it's going to be. I would assume that it's going to start from 2 way above. So if I hit play, it's coming from way above. If you want to just see the entire picture, you hit this, and you can see now that it starts at 2, and it has a velocity that's going upwards, and then it comes down, right? Let's say I set the initial velocity to be 0. How would you expect this to behave? My guess is that it would be having an initial tangent that's horizontal, and then it will come down. So let's see if my guess is correct. And it is. So the tangent here is 0, and then it comes down. Now, what if I want to estimate how the system will respond if I am providing an initial condition that is half? So let's say this becomes 1. My guess is that everything is going to become half. So at every instance of time, there's going to come down to half. There's going to go up by half. Whatever was this distance is going to move up by half. And the reason for that is because this is a linear system. So let's hit play. And I see that happening. So Simulink makes life quite easy in terms of understanding and visualizing system response and so on. But all of this was with just initial conditions. So we're playing with just that. Let's introduce a force to the system. So I'm going to share my iPad again. Yep. I hope you can see this is now. Okay. So if let's say we had a force acting, um, let's say the force is a step function. So on the right hand side, we would have h of t. Now, this here is why I said when you're building that system block diagram, don't divide by 6 and then have nicer numbers, because if we did that, then we'd have to start again. We'd have to move all of those. I mean, we have to make sure that whatever we canceled, we account for it and so on. I hope you got that. But since I didn't do that, I can just account for this here. So now my system has another signal coming in here, which can easily be accommodated by first defining that system. So there would be an h of t coming in. This is the force coming into the system. or whatever input is coming into the system. And this here is the system, right? So it's a good idea to have a place for external inputs coming in here um, at the top and having your signal coming in all the way from the left. Just good practice. So now you have this h of t signal coming in, and all you have to do is connect this here. So implementing this in Simulink would be super easy. Let's see how that works. So all you have to do is you want to define a plus before the minuses. Give me a second. So um, you see that the signal has moved, right? And that's an issue, so you need to create it again. So in this case, just drag it around the position you want it to be in. And then now you want to create that h of t function, which is a unit step function. So if I type in heavy side, does it work? No. So then let's try another word. Unit, there's unit delay. What about unit step? Nope. So then let's look at step. Okay, so a step function. Well, actually, you can do Google as well. You can Google what is a unit step function in Simulink, and you would find step. But instead of just connecting it, let's say that I'm not sure that this will work. If you want to see how the signal looks, you can just put a scope there, and you can visualize the signal first. So this here is exactly what I expect. It's a step function, but it's stepping in at 1, which is convenient because so far everything that we looked at was a step function at 0 only. But now in Simulink, we can vary that because Simulink has more features. Or maybe that's a simplification, but there's ways to do this by hand as well, but we're not going to be learning it in class because Simulink is there to help us. So step function, the options are step time of 1, initial value of 0, final value of 1. So we can change this if we want. We can make the step time 2, going from a value of 0 to 10. So all of this can be done by hand as well. So now we have this step happening at time 2 and going to 10. And let's just connect that to the system and then see how the system behaves. So in this case, it's coming down from that initial position of 1, coming down. That's basically the free response, because if you look at this signal here, there's no input, right? So until 2, it's basically free response. And then at 2, it starts experiencing that step function effect. And so now it starts rising up more than if it was just free response. And then it settles to some other position. Now, there's also a stable response, but we do not talk about stability of a system based on forces. We can only talk about the stability with the initial conditions. Okay. So I hope this stuff was fun. Let's just play around with some other functions. Let's say we want a ramp function. Okay, so ramp straight up is available. So options are the slope. Let's say we want a slope of 2 and we want it to start at a time of 2 again. And we can even change the initial output. So can have, let's say, 1.5. So because I don't fully I'm not sure how it's going to respond, how it's going to provide a force. I'm going to look at it first. Here's the scope. And yeah, so it is kind of how I expect. So it's starting at 1.5, it's staying there, and then at 2, there's now a slope of what is that is defined? A slope of 2. So this is now the input coming into a system. And let's now look at that response. So the system has a different response as compared to a step function. And you can see that it's going up, right? All this time, we didn't change the setting of how long should the simulation be. But I think if you're observant, you would have seen that there's a stop time here. You can just type in, let's say we want to go for 100 seconds. And then you go here and you hit this. Now you see that it's showing a much larger time frame. So is this response stable? You can't say it because stability is only for the initial conditions. Never forget, you can always have a force that makes your system go to infinity. Okay. So this is just how the system responds to a ramp input, which makes sense. It's like whatever forcing function is there is continuously increasing, so your system is going to keep going to infinity. What about some other functions like, let's say, sine? Okay, so there is one, but it requires an input. Hmm. So what would be the input to a sine block? You can Google it, but I know the answer. It is you can provide time. Oh, sorry. Time was not it. Clock. You provide a clock. This is acting as the time vector. So it's like time as the simulation is happening. Whatever the time of the simulation comes in. And what should be here is sine of that time. So let's see if that makes sense. I'm gonna create a scope and let's just run it. Wait a second. That doesn't look right. Does it? Not at all. We know what sine functions look like, and this does not look like it. So what just happened? If you go to the model settings, okay, I'll be slower. You press this button here for prepare. You go to model settings. By default, Simulink uses a variable step solver, which is very efficient. What it does is in regions where large changes are happening, it makes small steps in time. I'm not going to go into the details because I believe you've learned this in 2850, but so you switch to a fixed step. And if you choose something with like ODE4, ODE5, and then we run it, it doesn't care anymore about how much of a change is happening. So fixed step typically will give you more reliable results. The other thing is the step size. Again, this is automatic. So let's now change this to something small, like a step in time should be 0.001 seconds, let's say. And then let's look at the scope. That looks so much more like a sine function. See that? So in general, when you are building a system, keep your model settings as fixed step. If you really need to, if you're going to variable step, go for ODE 45. I would recommend keeping fixed step. ODE 5 or 8 is also fine. Like the higher the number, it's basically how many steps are you actually considering? Oh, that's stuff with 2850. I'm not going to go into the details, but ODE 5 should give you good results with a small step size. So this here is what I expect from the system. So this is what I consider acceptable sine function. And if I now hit play, look at that. The system starts at 1, comes down, and then you see these oscillatory motions. And that's again what I would expect from the system. Easily, you can change it to sine, cosine, tan, a sine, all of these. Whatever's the input, it's going to be sine of that input or cos of that input. Let's just switch it to cos and see what happens. So you see that this dip was not there before. So because of a change in the phase, because sine and cosine are just 90 degrees phased out, you see that there's a difference here. But given enough time, you see similar behavior. Okay, so we've been having fun with this. There's one more function that we need to look at, which is exponential. So I see exp. Let's look at that. So e to the power u. Now in class, I said that a lot of times u denotes the input. So if I were to guess, I would say that if I put this in here, and oh, that's a pretty cool feature, right? I can just move it in there, and Simulink understands that it has to wedge that in there. So now double click and I type in scope. And okay, so in this case, it's an exponential function and it is going up to 10 to the power 43. Is that what you expect? Yes, because this is e to the power t function. What we've been looking at and calling as the decay function is e to the power minus t. So let's create a gain of -1 and look at that. It wedges it in between. So now in this case is e to the power minus, so this clock here, think of it as just t. So e to the power minus t is what's going to be created by this block here. And if I were to look at the signal, it starts at 1 and it decays. Exactly what I expect. For fun, let's look at what is the output. Yeah, so it's like in the beginning there was some signal and then some input, and then that dies out, which is why it comes back to 0, its resting position. So I hope this was clear and fun. Now, you probably noticed that I keep deleting this. It's just good practice. When you're creating a scope and the scope has done its job, delete it because the next person who is looking at your Simulink model doesn't need to know what you are thinking of. And I believe scopes, I don't know if MATLAB did an update, but scopes do slow down your Simulink from what I know because it has to log each of those data points as it does the simulation. Okay, so with that, one bit of Simulink basics is done. Um, it appears that I have there's some slowness in switching to the iPad, so I'm just going to sketch some basic things here. So let's say that we're interested in a function that looks like this. So at some time t is equal to 1. Let me just mark this as well. This time t, there's some function f of t. I want signal that looks like this. Till 1, it's at 0, and then it jumps up, and it jumps up to a value of 1. And it stays at 1, and it drops back down to 2. Sorry, drops back down to 0 at 2. So I want to now create this signal. What do you think is a good way of doing this? This is honestly, I hope this is a lot of fun. It is for me. It's basically like you have building blocks or you're playing with Lego and you have an objective in mind and you have a certain set of tools which I kind of took you through is you have step functions, ramp functions, exponential functions, sine functions. There's so many of them. I want to build this based on the tools that I shared with you. So if you want, you can pause the video and think about it and then get back to what I'm going to show you now, which is the answer. So if I were to create one signal that has a step function happening in this way, is going from 0 to 1 at a time of 1. So this is one step function, right? I can double click, I can provide the input time as 1 and the change from initial value of 0 to 1, and I've got this. And then a second one that looks like this. Well, actually, let me do that again. A second one that actually goes negative. So it starts at 0 and it stays at 0 until 2. And at 2, it drops down to -1. And then it stays at -1. So now um if I were to add this signal and this signal, I would then have until this point, both signals are 0. That is that's the signal that I desire. So that's fine. And then from here, this signal is giving 0 value. This signal is giving 1 value, which is now the signal that I desire, which is 1. Now from 2 onwards, this signal is still at 1 because it's a unit step function. I mean, sorry, it's a step function, so it stays at that value. And at 2, it goes down here. And so now if you add them together, it's +1 -1, 0. So I can represent this signal that I'm interested in by the sum of this step function and this step function, which you have the tools to build in Simulink. So let's just do that. So another cool thing about Simulink is you can comment out Simulink blocks the same way that you comment out code. So let's say I'm not interested in this, so I can comment it out, move it aside, I can take out the signal. So now later on, if I want to move this in, I can just plug it in there and it's fine. Not the best practice, but useful for beginners. So I want to create that signal, right? Give me a second. My system is low battery. So in this case, I have a step function and another step function, and I want them added together. So I have this here coming in together. I'm honestly having fun doing this. Um, I would like to have a scope so that I can see what's happening. And we kind of sketch it out. So the first one is a step that happens at 1. It goes from 0 to 1. Let's do that. Step happening at 1, going from 0 to 1. That's good. The second one is a step that's going from 0 to -1 at 2 seconds. So 2 seconds going from 0 to -1. The scope, it is what I expect, which is 0 to 1, it has a value of 0. 1 to 2, it has a value of 1. And 2 to infinity, it has a value of 0. So now that I confirm that this is what I want, I can connect it here. Always a good idea to tidy up. As things get more complicated, these little things matter. The cleaner that it is, the easier it is for your mind to wrap around what's happening in the figure. So in this case, let's look at that system. So it has a different response as compared to just a unit step. So in the beginning, it's just having free response. Actually, I don't like that it's going all the way to 100, so I'm just going to change this to 10. And then I hit this. And now we can see first it's the free response is coming back towards zero, and then it's going to go to the step equilibrium. And then there's that other the step function is acting, but it looks like the step function is not doing a whole lot. So it might be that the way that the system parameters are, if you look at this is 18, that's 36. These are much larger. Perhaps that's the reason why you don't see that much of a difference. So what if we increase the value from a 1 to, let's say, 100? Let's do that here as well. Now look at that. So in the beginning, it's free response. It was coming back to zero, but you now have a step that is pushing it all the way up. But that step was only there from 1 second to 2 seconds. And so now it shows that coming up here, and then at 2 seconds it's taken off. So there was that initial velocity there, right? Because there is some inertia, it is moving upwards. And because of that initial in the velocity that exists with whatever object it is, it still continues to move up a little bit. It's like if you take a snapshot at 2 seconds, it's like there's an initial velocity that's upwards because of the fact that it was moving in this way, and then it comes back down. But as you can see, sometimes you want to see more than one signal in a scope. And the cool thing is you can just drag a new pickup point to that scope. And if you hit play, you can see both of them. Simply because there's a large figure, I feel a little lazy, and I'm going to just add a gain of 1/10, drag it in there, it fetches itself. So now this is the new input, is whatever was the step function being added together and so on, what is the output is divided by 10. I'm going to give the signal a name, f of t, as the, um, should be able to drag this, yeah, as the signal name, and it's coming into the scope. Now what I'm hoping is that the scope shows the name, but it doesn't. And to do that, you need to go to View, Legend, and now you have the two signals. So in this same scope, you have your X in the blue line, and then your signal input as the yellow line. And if I make this 1/100, you will see the same that we saw in the beginning, which is, yep. But now you can understand why it is a much smaller effect. I hope this was clear. I do have more content to cover. So let's say now that I'm going to try and switch again. So not smooth. Okay. So this was now the system with this input. And we played around with a lot of functions, so you've got a lot of experience with that now. Let's say that, okay, I'm sure that at this point you guys know how to deal with h of t plus g of t. It's basically like you have some function h of t coming in. So h of t is, say, a step function, and g of t is a ramp function. So there's h of t, there's g of t. Now these signals are coming in as blocks from Simulink, and then you just add them up, and that becomes your input. And I'm sure you guys know how to do this. So the other thing I need to show you is, what if it was h dot of t plus 2h of t. You can pause the video and think about this. You basically have to convey this information to Simulink, right? So the easiest way to do it is you take the Laplace transform of the right-hand side. It'll be h of s times s plus 2, right? So as I mentioned, Simulink is seeing everything in the Laplace domain. So if I were to draw h of t as a signal, in fact, Simulink is seeing it as h of s. It's like it needs to be multiplied with s plus 2, and that becomes your h dot plus 2h signal. So I hope this is easy to see, even though we're marking this as h, and that's common practice in Simulink development. The signal is actually h of s, and so h of s is multiplied with s plus 2, and that gives you the desired signal, which is h dot plus 2h, which is now your input coming in here. So h dot plus 2h. Okay, so with that, I've covered most of the Simulink content in terms of how to build different blocks, how to combine inputs, and so on. The other thing is, what if you have two systems? And I'm just going to do it on this iPad. So you have, let's not say two systems, two masses. So I'm going to actually pull up equation of motion from the class, which is, let's say, the case where we had those two. Okay, this, yeah, I'm not able to switch between the iPad and the computer, but trust me when I tell you that one of the equations of motion was m1 x1 double dot. I'm just going to assign values for the, no, I'm not going to assign values. So m1 x1 double dot plus c1 x1 dot plus k1 x1 minus c1 x2 dot is equal to 0 is one equation. And the other one is m2 x2 double dot plus c1 plus c2 x2 dot minus c1 x1 dot plus k2 k3 over k2 plus k3 times x2 is equal to f of t. So these are the two equations of motion for the two masses. Let's very quickly build it. So we would have x1 double dot is equal to, so I'm moving everything to the other side. Never forget this. There's a 1 by m1 constant. c1 x2 dot minus k1 x1 minus c1 x1 dot. So I just took care of this. I took care of that. x2 double dot is equal to, and I'm going to move everything to the other side. Never forget this. It's f of t minus k2 k3 by k2 plus k3. Don't worry about standard form here. This is for us to communicate to the computer. So we have these two equations. And now we need to kind of bring this to Simulink, which, if you notice, there's an x1 term, there's an x2 there, there's an x2 term, there's an x1 here. So I think this is very easy for you to see that you're going to have two integrands. So there's going to be 1 by s. Actually, let me color code this. This here is going to be in black. So the first one is the x1 double dot integrated to get x1 dot. integrated to get x1. There's the first building block. Second one is x2 double dot integrated to get x2 dot integrated to give x2. So these are now the signals that we can play with. And of course, there is also the input f of t, which we'll deal with. So let's start with this equation here. So I'm going to start with putting in that constant here. So just so that I don't forget it. It's a constant. It's difficult to put a triangle, so I'm just doing it this way. And then you have three terms. So plus, minus, minus, plus, minus, minus. And the first term is C1 x2 dot. Wait a second, it's x2 dot. So you have to take it from here and then somehow you have to bring it here. All you have to do is put in a gain, putting that here now. It's going to be C1 x2 dot, right? Because we already created all the signals. We have everything we need. We have the building blocks. We take a copy from x2 dot, multiply with C1, and it goes up here. So that's C1 x2 dot taken care of. And then we have minus K1 x1. So that is coming in from here. I'm going to be a little better at doing that. It's K1 x1 coming in. And let's apply that there. And the last one is C1 x1 dot. So pulling it from here, coming in here. I did that there just to make sure that it's clear to see that it's not related to the signal, this signal that's crossing. So this is x1 dot that have come in. I'm kind of drawing it like how I build in Simulink, which is I know that I can just wedge a gain in between. So in this case, I'm going to be wedging a gain of C1 x1 dot. At this point, we have C1 x1 dot with a negative sign, K1 x1 with a negative sign, and C1 x2 dot being added together and then multiply with this constant. And that is what we're claiming is x1 double dot, which has captured this equation here. Now, I really think that you should pause and try to get the rest of this done by yourself before you watch the rest of the video. So now we need to tackle this guy here. So this one has 1, 2, 3, 4 terms. I'm just going to create a block which captures the relations. So there's a plus, minus, plus, minus. The first one is the forcing function, f of t. F of t can be anything. So as I showed you, you can design it as a step function going up and down. It can be a sine function, exponential decay, whatever it is. And the next one is a big constant multiplied with x2. So I'm going to write down that constant here. It's K2, K3 over K2 plus K3. There's a block. It takes in a signal from X2, which I'm supplying here. It's being multiplied, and that is your signal. So it's K2, K3 over K2 plus K3 multiplied with X2, and it has a minus sign associated with it. And then we have C1 X1 dot. If you see, we've actually already obtained that signal here. So instead of creating a new dropout and then creating a connection there, you can just take from that signal again. So in that case, I'm just going to do this. So we now have C1 X1 dot arriving at the destination with a positive sign. And then we have the C1 plus C2 times X2 dot. So I'm going to write that here as C1 plus C2 within a block. And coming in here. Oh, in Simulink, this would be rigid lines like that. In general, block diagrams don't have curves. I don't think it's a law, but I've never seen a block diagram with curves. Okay, so now at this point, we have all of these terms captured. I forgot to put that. So I need to do a 1 by M2. And then this stuff that's been added is multiplied with this. And it gives me what is X2 double R. So with this, I have captured this relation, which I believe is from the multi-degree of freedom set of lecture notes. Yeah, it is 30th August, lecture 5, multiple degrees of freedom, page 7 of the lecture notes. So I've captured that. And I think with that, we can end the content of today's lecture, virtual lecture. I hope that this was useful. I will probably upload another shorter video in which I show you good practices of how to submit a Simulink model to anyone, how to define these parameters. If you want to be building this right now, you'd likely be putting in values of M1 as 1, C1 as something like 2 Newton second per meter. This is something like 10. And then you'd be putting in those values here, right? The thing is that if you put it there, it's called hard coding, but in reality, which is not a good practice in coding in general, in reality, you might want to be changing those parameters. And sometimes you will have C1 appearing in multiple places. And then you're setting yourself up for failure if you go and put in those numbers everywhere inside the Simulink model. So what we did here is basically not good practice. What we should be doing is in our MATLAB workspace, we should have the variables as something like um, M1 is equal to 1. This should be defined in a script, one, and then you should put it, I mean, you should always define the units. So in a comment, you need to say what is the unit, and C1 is equal to 2 in a comment, like uh, Newton seconds per meter, and so on. But yeah, that is a good practice. I'll make a short video to get you through that. But for now, I hope you guys have fun with Simulink. I think you can see that there's a lot of intuitive features that should help with the experience. So with that, thank you so much for your time. I hope I was not too slow. I hope you guys had fun. Thank you.